Okay, finally we are going to see a bona fide example of an E1 reaction, and we had to wait until we learned about alcohols to do it. So remember, E1 occurs because we're going to form a carbocation, and that carbocation is not going to be attacked. Normally if you make a carbocation and there's any nucleophile, it's always going to be weak. If there's any nucleophile, you will do an SN1. So the trick to doing an E1 reaction is to make a carbocation and have no nucleophiles around. And if there's no nucleophile, then you're going to lose a beta hydrogen and get your elimination product, your E1 product. So remember, we're going to do this reaction on an alcohol. So we have to protonate our alcohol. And let's draw one. We need to protonate this alcohol and yet not have any nucleophiles around. That means we can't use, for the E1, we can't use acids like HCl because that forms Cl-. Cl- will attack a carbocation. We can't use HBr. We can't use HI. All of these are off the table because all of these halide counterions will attack our carbocation. What are the only two acids that we'll use? Are H2SO4, sulfuric acid, and phosphoric acid, H3PO4. These are non-nucleophilic conjugate bases. The bisulfate and the biphosphate are non-nucleophilic. So here we go. Let's throw this in, sulfuric acid. Now this isn't sulfuric acid and water, because water is a nucleophile, and water would attack a carbocation. This is concentrated sulfuric acid or concentrated phosphoric acid. So the first step is protonation. Now with acid, but we're not going to use H3O plus or protonated methanol. There's no methanol or water in here. We protonate, convert our OH to a molecule of water on the side of our larger structure. This is now a great leaving group, and that was the purpose of the acid. This will leave. That oxygen will get the electrons it wants, and will form a carbocation. Now, as always, we can only do this if we're going to form a good carbocation. And in fact, often these are kind of sluggish, so people will actually heat this up too to get this to occur. But now we formed this tertiary carbocation. This carbocation, two fates of a carbocation. They get attacked or lose a beta hydrogen. We don't have a nucleophile in this case. So what do? We lose a beta hydrogen. Our alpha carbon is the carbon bearing the charge. This makes that a beta carbon. Now, of course, we have other beta carbons as well. But I'm just going to highlight this one on the end. And now I'm going to be a little evasive. To remove a proton, I need a base. But clearly we don't have any strong bases in here. It's not like we're going to talk about hydroxide. So I'm just going to say some base, unnamed base, some good Samaritan base is going to come along and do a favor and pluck off this hydrogen. Now, hydrogen already has a bond, so to make a new bond, it needs to lose an old one. It only has one. It's that CH bond. And that bonding pair is going to lean over, form our alkene between the alpha and beta carbon. Now we've formed our new alkene, and we've done our elimination. And not just any elimination, an E1 elimination. Now, since we're working with carbocations, you have to be aware of the tricky things that carbocations could possibly do. Anytime you do an SN1 or E1, you need to say, oh, could I possibly do a rearrangement? Since we're doing a tertiary carbocation, there is no rearrangement possible. But here is an E1. E1s are very common with alcohols. They're used on industrial scales and laboratory scales, unlike halides, which almost never do effective E1 reactions.